My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda and School of Astrophysics and Astronomy and YouTube channel Pretam Kumar Das, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from Canada. So hope you are well and safe from corona pandemic. So as we all know that we are staying in a corona pandemic situation since March 2020. We cannot continue our normal academic program due to the corona pandemic. So we have to start our online program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, has started this online program, including a new thing, International Physics Webinar, and we have successfully completed our 153rd International Physics Webinars, including two Nobel laureate speakers, and today it's our 154th International Physics Webinar. So we are trying to adjust with this new normal situation. So today I'd like to welcome you all through a joint session between our Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Lethbridge, Canada. And we have with us here today Dr. Arundhati Dasgupta, Madam, Associate Professor of Physics, Department of Physics and Astronomy, University of Lethbridge, Canada, and she has already connected with us. So I'd like to welcome our speakers. Madam, good morning and good evening here. So thanks for accepting our invitation, madam. So it's my honor and privilege to host you in my International Physics webinar, madam. So for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, I'd like to introduce our speaker, all of you, and then our speaker will deliver her speech. And at the end, we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting also. So I think you have already come to know the title of this today's international and title is A Time for Quantum Gravity Phenomenology. And our speaker is Dr. Arundhati Dasgupta, Madam, Associate Professor of Physics, Department of Physics and Astronomy, University of Lethbridge, Canada. We can see his, before going his details, so we can see the abstract of this title of this talk. So the discovery of photons, the quantum electromagnetism waves followed decades after the time of complete formulation of Maxwell equation. In this talk, we discuss the plausible ways to test for the existence of the quanta for gravitational waves essentially after the formulation of general relativity, theory of relativity, and a few years after their discovery in LIGO. A new observation due to the discovery of gravitational waves in 2015 shed light on graviton mass bound. Theoretically, graviton interaction are non-linearizable, and we discuss non-perturbative calculation of the graviton physics. So we also provide an overview of the current status of experiment which seeks verification of phenomena like Hawking radiation and other quantum gravity predictions. So we can see her academic and previous position. So we can see our madam completed her bachelor degree in physics from Presidency College, Kolkata, India, and her MSc degree in theoretical physics from Anna University and Institute of Mathematical Science, Chennai, India, and her PhD, University of Madras and Institute of Mathematical Science, Chennai, India. So her previous position, she joined as a junior research fellow at the Institute of Mathematical Science, Chennai, and she stayed there 1994 to 1999. Then as a postdoctoral fellow at Max Planck Institute of Gravitational Physics, Germany, 1999 to 2002. Another postdoctoral fellow at University of Liver de Brussels, Belgium, 2002 2004. Assistant professor at the University of New Brunswick, Canada, 2004 2006. At the same university, associate professor 2006 to 2008. Now she's also working as an associate professor of the Department of Physics, University of Lethbridge. So this is her research field: theoretical physics, quantum gravity phenomenology, black hole physics, astrophysics, gravitational waves, quantum field theory, supersymmetry and supergravity, gender and physics. And this is his fellowship and honors. So first class and distinction, MSc 1996, first place in the integrated PhD program, Institute of Mathematical Science, Chennai, and ICTP visiting scholarship, Abdul Salam International Center for Theoretical Physics, Trieste, Italy, in 1998. Nominated and chair elected, Division of the Theoretical Physics, Canadian Association of Physics, Canada, 2011. Honorable mention of Gravity Research Foundation, essay competition for paper co-authored with student, 2012, and chair Division of Theoretical Physics, Canadian Association of Physicists, 2013. And this is her grants. So this is her, it is per HEP ID, and this is her Google Scholar ID. So her citation is more than 550, and this is her publication list. She has a more than 50 publication in different international journal, and this is her list as an invited panelist, and this is her books, you can see. So thanks for all of your patience. Now it's time to go to our speaker. So madam, I'd like to welcome you again. So it's your time, madam. You can start your session, and thanks for accepting our invitation again.
Thank you very much for the invitation. I found just today that Pretam had applied in 2013 for a PhD position in the Department of Physics and Astronomy to my address, but probably had not replied to that. So in future, I would welcome any students from your university.
Yeah, of course.
Definitely, I have a lot of, we have a lot of students from Bangladesh studying here. Also, my very close friends are from Bangladesh, and I talk to them about science as well as other social.
Yeah, that would be very great things.
Because we are all Bengalis, and
yeah.
In fact, on pen and paper, I've been the supervisor of Hoimonti Rosario. She's from Bangladesh. So her thesis was in molecular spectroscopy, but for some formal reasons in the university system. So I know her very well. I was her thesis examiner. And also, before I start, I wanted to say some things about women and their contribution to physics. And that is why I had asked Pretam to highlight my book, Gender, Feminism, Physics. It is a book about women and the underrepresentation of women in physics. There are very few women in physics. I went and saw your web page, Pabna, University of Science and Technology, and there was only one woman in the department, which is true even here. So there are parallels everywhere. But if we look at the population, then women should be at least 30% of the faculty be represented in the physics profession more than what they are now. So there is a sort of belief that women do not like physics, but that is not at all true from my personal experience. And I'm telling this from a very practical point of view. From my personal experience, it is not something didactic, or it is not quoted from some big book, or I'm not saying something which is very, very scientific, but it is not based on scientific data, but it is something which I think all of us realize in our ways of living, and that is doing physics is much easier than giving for a woman than staying at home and cooking every day. That is much, much boring than studying physics, which is very much exciting, and then maintaining a home and bringing up children. So physics is much, much easier than that. And believe me, all of you are probably aware that studying physics, writing research papers in physics, making discoveries in physics is an easier job than staying at home and maintaining young lives. Also, I would like to say that women have diverse capabilities. They are really very, very talented human resource, and to make all of them cook at home and bring up children, it is really one of the reasons I think we have so much of strife and wars in the world. If you let women do whatever they are born for, then the world would be much peaceful than it is now. I would like to give an example for everyone, and that is my school, my um, batchmates, the best student in physics was married off at a very young age. And instead of becoming a world-class scientist, she now teaches science to school students. So we are losing human resources and human talent when we force another quote unquote work on someone who is meant to do science or meant to do physics. And another example is my younger sister. She was very much interested in sports, but we did not allow her to become a sports person. So instead of having a world-class sports player, we have at home a person who is a journalist and a freelance journalist. And the reason I'm mentioning her is that she now writes children books. And yesterday, she gave a link to a children's book on ECG Sudarshan. ECG Sudarshan is a very well-known Indian scientist. He was nominated 9 times for the Nobel Prize. And it is said that maybe there was some sort of partiality in the Nobel Prize committee that he did not get the Nobel Prize. But when I was reading her book on ECG Sudarshan, I realized that he got interested in the V-A theory, for which he is famous for and for which he was nominated for the Nobel Prize, because he interacted when he was a young student with Marshak at TIFR in India, in Bombay. He interacted with his future collaborator, and he got to know about science and the importance of the quantum field theory because of his interaction with older faculty at a very young age. So that is one of the reasons I would like to start my talk now. And I hope that you can see my slides because I can't see the screen. Pretam, can you confirm that my slides are visible?
Yes,
Okay.
yes, madam, you can see.
Because I can't see the fine. Screen. Pretam, can you confirm that my slides are visible?
Yes, madam, you can see.
Because I can't see the fine.
Madam,
Okay.
there is echo.
Yeah, sorry. I just wanted to confirm using my mobile that I'm online. So I will start the talk. And what I will talk about is quantum gravity phenomenology. And my claim is that we, as a scientific community, are ready to talk about this very important aspect of fundamental science. Now, why I'm saying that, and that is because we are aware of the cosmic microwave background, and this cosmic microwave background is remnants of the early universe cosmology, interactions in the early universe, which did have quantum mechanics of gravitational degrees of freedom. And even though today we see gravity as a classical phenomena, the remnants of the past have information about the quantum nature of the gravitational interaction. So there is quantum gravity indirect evidences of quantum gravity in nature around us, and we should be able to find these in the fine print about the physics of the cosmos. Now, another reason why it's very important that we start exploring the unexplored, and that is because when we try to predict the future, we have various predictions about what our cosmic evolution is. And in that story, about 68% is dark energy and 27% is dark matter. And these are invisible ingredients in the cosmic evolution. If most of our cosmic story is unknown, not yet detected, and only 4% is visible matter, which we see on Earth, then we have to really gear up and work towards finding more fundamental aspects of nature. Now, the story which tells us about our cosmic evolution, or the fact that only 4% of nature is known to us, is due to Einstein. This is Einstein's equation, which you can see, and the symbols r mu nu minus half g mu nu r are basically curvature of space-time. They have information about how our cosmos is curved, whether it's like a sphere, whether it's like a hyperbolic space-time, or whether it's like a open flat geometry. And on this side, we have the energy momentum tensor of matter. It's a 4x4 matrix, so it's a 2-indexed object. It's a 4x4 matrix, and it has information about the mass, the energy of the matter which causes this cosmic evolution. There's also the cosmological constant term. The cosmological constant is something which is intrinsic to the fabric of our space-time. And together with the cosmological constant and the matter, we create our universe. Basically, we started from nothing, that's the story. And then slowly we evolved to our current epoch and the large-scale structure. This story requires, because of the fact that the universe is accelerating, that 96% is still unknown. Now, what is this equation? What is the story of Einstein's equation, which is also quote and unquote general theory of relativity? And why we should probe it further, why we should know much more than what we know today, is what this talk is all about. And I will try to argue that we need to probe some experiments and take some of the calculations which have been there about the nature, true nature of quantum version of this equation seriously, and try and write a new story of general theory of relativity. Now, why is there general relativity? I know that you have had a lot of speakers about gravitational physics in this series, but I will still try to motivate it, because one of the crucial aspects of quantum theory of general relativity would involve the basic formulations of this theory. Now, why did Einstein write a theory of general relativity? In 1905, Einstein published the paper on electrodynamics of moving bodies. And this was one of the first papers which talked about the theory of relativity and the role of the observer in measuring the universe. So all our nature exists in front of us. We try to probe that nature using measuring instruments. And when we do that, we have preferential reference frames. When we have two reference frames which are moving with respect to each other with a constant velocity, then the usual common sense laws of Galilean relativity are not true, but one has to introduce what is known as the constancy of the speed of light. The speed of light is the same for all observers, and to introduce this law, one had to change the rules of transformations of measured quantities from one reference frame to another. And this caused some strange things like time dilation, length contraction, which probably all of you have heard about. But it agreed completely with Maxwell's equations and the theory of light. Electromagnetic waves are light, and that is how we see the world or measure the world using light, electromagnetic interactions, and the flow of electromagnetic energy is the causation of most phenomena around us. But there was still the other theory, the theory of gravity, which people were aware of at the time, and that was not compatible with special theory of relativity, which was the theory of inertial frames. But also there was the question, why would we stop at the story of observers related to each other using constant velocities? We should also ask the question, if we have accelerating observers, whether their perception of nature would agree. And that is where Einstein had to introduce what is known as curved geometries. And the reason was very simple. If we have a rotating disk, then when the disk rotates, the disk particles have velocity. Because of special theory of relativity, different particles at different radii from the center of the disk would have different velocities and different lengths, because there would be length contraction. And this is what the metric of the rotating disk is. Usually, if it's a static disk, this is just r squared d theta squared. That is the length of an arc along circumference at a distance r from the center. But because now we have special theory of relativity, the arc length gets contracted by this factor. And this is r omega, that's the velocity of the particle at a distance r from the center. So it's as easy as that. And Einstein realized that now the ratio of circumference to radii, which is usually twice pi, would no longer be true, and the disk would be a distorted disk. So he had to introduce changes in geometry, Euclidean geometry, to facilitate his special theory of relativity. And this rotating disk was the accelerating disk, because obviously we know we can cause rotation only when we have centripetal acceleration. Rotation is not motion, linear motion without an external force. Rotation is a accelerated motion, and therefore it is something which has acceleration in it. And Einstein came up with the theory of curved geometries, where acceleration or accelerated observers get naturally included in the description of the system. For example, if we have flat geometries where there's no acceleration, then this would be a flat geometry. Here, if we draw two parallel lines, they never meet. So that is also a measure of whether a geometry is flat or distorted, and whether a system has acceleration in it or it is at rest. If we have these two parallel lines and we measure the distance between them and it remains constant, then we say we are in zero curvature geometry, and it's known as geodesic deviation. So when we study the distance between two different parallel lines in geometry, we call it geodesic deviation. Geodesic is the trajectory on a geometry which connects 2 points on the geometry with the least distance between the 2 points. Now, if we have curved geometries, the story changes. If we have an orange, or let's say our Earth, then the parallel lines, if we start at the equator with two parallel lines, they will always meet at the poles. So that means that this story of geodesic deviation is true whenever we have the deviation changing with the location at which we are measuring the geodesic deviation. We have curved geometries, otherwise we have flat geometries. So using this notion of geometry, which is known as Riemannian geometry, Einstein came up with his theory of gravitational physics. Now, most of us think that Einstein formulated his theory of geometry and physics all by himself, and it's not true. Marshall Grossman, Michael Besso, and Mile Valaric all contributed to his theory of general theory of gravity. And in 1915, over a time of 15 years, Einstein was able to formulate the theory of gravity. And today, it is one of the strongest theories known in nature. All the predictions Einstein had from his Einstein's equations, where there is Riemannian geometry of space-time on one side, and on the other side, there is matter, energy, momentum, has been tested to be true. For example, there are phenomena like gravitational lensing, and this was predicted in 1912. It's always surprising to see how correct general theory of relativity is. For example, the double quasar is actually double image of one quasar, and this was predicted as early as April 1912 by Einstein using his theory of general relativity and the concept of gravitational lensing. And we see this in experimental confirmations from astrophysics today. Then we have, if we see the future, predictions of time warps and wormholes. These are all bizarre and new predictions of the theory of general relativity, which we had not anticipated. And it is based on that Einstein equation, which relates curvature or Riemannian curvature of space-time or our cosmic universe to matter. And this is what we now realize is the theory of gravitational physics. So if we have time warps and wormholes, then obviously we would be able to have time machines, and we would be able to travel forward in time as well as backward in time. So that is one of the very important predictions of the Einstein theory of general relativity. And some of us here, including a summer student, Kimberly, are working towards finding realistic causation of time travel. Then, of course, the very surprising discovery in 2016 of the science of gravitational waves. These are very weak compared to the large scale. The gravitational waves are very weak in amplitude. That's about 10 to the power minus 21 in magnitude, and it took about 100 years of extreme sensitive detector building to be able to observe gravitational waves. But it also tells us that the Einstein equations are very correct in their sphere of validity. Now, for the future, there's also the possibility of energy extraction from black holes and stars. Black holes have become realities now. There were 3 scientists who were awarded the Nobel Prize last year based on the science of black holes, which is also another bizarre prediction of general relativity. Everything which falls inside a black hole is lost to the outside world, and we cannot see inside a black hole because light cannot escape the black hole. And what we basically see is the accretion disks and the light or X-rays which surrounds the black hole. And today, of course, not just based on the observations of Andrea Ghez and co-Nobel laureate, we also have the image of the event horizon, which was announced in very recent work by the Event Horizon Telescope collaboration. So gravity, which is not just the story of the apple falling from a tree as perceived by Newton, is much more in scope. It is the story of our cosmos. It is the story of many phenomena which we find bizarre, like black holes, gravitational lensing, which have been verified. They predict time travel, wormholes, and also we have now the very, very precision measurement of the gravitational wave. However, this story is all about classical gravity, where the length scales are not yet quantum. Now, what do we mean by the story of quantum gravity? And this is where, again, the precision nature of the physics comes into play. The gravitational quantum would be important at length scales of 10 to the power minus 35 meters. So that is why we are not yet talking about quantum theory of gravity. 10 to the power minus 35 meters is not zero, but it's minuscule. And that is called Planck length. Symbolically, it's written as LP. The exact calculation of this is obtained using Newton's constant, G, which appears even in Newton's law for gravity. It's a very weak force. If we have an apple and an orange, they have gravitational attraction between them, but don't see them moving towards each other, unlike an electron and a proton, which interact electromagnetically, because the gravitational constant, G, is very weak. Then we have the Planck's constant divided by twice pi, which is 8 bar. And then we have the speed of light. All these form the dimension of length in this formula, and that is known as Planck length. And this is the scale at which the quantum nature of gravitational physics would become important. And we can see it is 10 to the power minus 35 meters. Also, unlike our perception of what quantum physics is, which is the story of photons, atoms, and molecules, in gravitational quanta, what is quantized is the geometry. Because after all, gravitational physics, according to Einstein, is the story of acceleration. It's the story which distorts geometry. And that distortion of geometry is caused by the matter, masses, and energy, which we call the gravitational interaction. So the quanta for gravitational physics would be geometric quanta, And there is a theory called loop quantum gravity, which has obtained the quantization of area, for example, and that's equal to Planck length square times integers. And this would be, therefore, an area of 10 to the power minus 70 meters squared. So that is a very tiny number. This theory is still kinematic. There's no dynamics in it. It's a frozen theory of nature, frozen in time theory of nature. But we can see that the story of quantum gravity is different from the stories of quantum mechanics, which we've heard till now. And therefore, we have to be very careful in its formulation. What is my talk today about? My talk is about the fact that perhaps it is not too early to talk about experimental evidence of quantum gravity, even though the smallest length scales we've reached in our accelerators is about 10 to the power minus 17 meters. And to probe the quantum nature of gravitational physics, we have to probe about 10 to the power minus 35 meters, which is way, way, way tinier than what we have seen in the interaction of quarks inside protons. Now, there is, however, a reason why I'm still arguing that we cannot sit tight and wait for the time to flow or time to be ready for the theory of quantum gravity or the experiments to be probing the tiny length scales of 10 to the power minus 35 meters. But we have to gear up and accelerate, and we have to ask questions, or we have to design experiments which will probe the true quantum nature of gravitational physics. And this is because we are always working with quantum mechanics based on the assumption that gravity is classical. So we are actually working with semi-classical gravity. That is, we have the gravitational interaction as classical, the length scales at which we work with, we can still trust classical geometries, but we have quantum fields interacting in these classical geometries. Now, this is rather peculiar because, as we know, quantum fields have quantum fluctuations, and these quantum fluctuations can backreact on the classical geometry, and our classical geometries can change due to the quantum field interactions. So it is the semi-classical regime which we will probe, and we'll see that indeed we have strange phenomena which would require a more deeper theory of quantum gravity to emerge. And if we concentrate on the level of experimental evidence which we have on the plate at this time, we would be able to understand the physics at 10 to the power minus 35 meters and the emergent phenomena due to the interactions at that length scale, which are manifest today. As we said already, we began the talk with the premise that the cosmic microwave background has information about interactions which happened at the early universe formation stage of the cosmos. And it's not just the CMB, we would have other indirect evidences of the theory, which is true at Planckian length scales, but nevertheless evident in our day-to-day existence. Now, one of the crucial things which we always somehow put under the carpet is that when we work with quantum fields in curved geometries, thermalizations is natural and entropy creation happens for the quantum particles. Hawking radiation is a phenomena which is a manifestation of that, and it can be explained by this thermal process of entropy production. I have worked on that, and that is very new work. And what is really very, very interesting is that unitary evolution, which is the statement of probability conservation in quantum mechanics, and entropy production are not the same. And a question which Hawking had raised for his theory of black hole evaporation is true even for the generic quantum field in curved geometry, whether unitary quantum mechanics and gravitational physics are compatible or not. And this question can be asked at the very basic formulation of quantum fields in classical geometries. So our basic premise with which we work with today is that nature is quantum, but that quantization is restricted to electrons, protons, quarks, neutrinos, photons. But gravitational physics is classical, and we can ignore the quantum effects of gravitational physics because, after all, we've not reached the Planck length. But even at the level of semi-classical physics, when we try to formulate quantum field theory on curved geometries, we find that the theory is not the same as the theory where the background is non-interactive and the background is simply a flat, non-gravitational arena of plane. In particular, the basic premise of the formulation of general theory of relativity is the inclusion of accelerated frames in the story of nature. And if we include acceleration in the theory of quantum mechanics, there is no unique global vacuum except for spacetimes with symmetries. And in the presence of black holes, we have non-unitary evolution and information loss. Just from the point of view of extreme curved system which has no symmetries, no time-like killing vectors, then there would be a foliation of the geometry using observers who are all accelerating with respect to each other. And from the point of view of quantum mechanics or quantum field theory, each observer would have particles which are thermalized in the other's reference frame. This is true for every observer who is accelerating or is not following a geodesic trajectory. If the observer is freely falling, then that observer sees nothing. So just from the point of view of how to interpret or how to understand quantum field theory, we come up with these strange conclusions. In particular, for the black hole geometry, one has the horizon, and inside the horizon, this is a diagram of the black hole geometry in what is known as Eddington-Finkelstein coordinates. And here we have a horizon which is emerging from a collapsing star. And what happens is that the light cones are forward moving outside the horizon and the light cones are trapped inside the horizon. So if there's a particle which is created out of the quantum field theory vacuum has particles and antiparticles being created and annihilated all the time. And if there is such a particle-antiparticle pair created near the horizon, one of it falls inside the horizon, it gets trapped inside, and the particle escapes. We have generated particles out of the quantum field theory vacuum. It's almost like creating or separating the particle-antiparticle pair using the gravitational field bias. However, we have the same phenomenon in electricity and magnetism. The particle and antiparticle remain. In case of presence of a black hole horizon, the antiparticle falls into the black hole and is destroyed at the central singularity. It's only the particle which remains, and this generates a stream of particles which are emerging from inside, apparently, the horizon, because as the antiparticle enters the horizon, it has negative energy, so the black hole loses some energy when it takes in the antiparticle, and the black hole starts shrinking because it's losing mass in the process of particle creation, and we have what is called black hole evaporation. And this is also a thermalized process. It's a scrambled process. It is not a pure evolution, and we can calculate the temperature of this process. For a solar mass black hole, the temperature is about 10 to the power minus 8 degree Kelvin, which is much lower than the ambient temperature, the CMB, which is 2.78 Kelvin. So therefore, we don't see black holes evaporating in the sky all the time. But if they were black holes which were primordial, or they were created in the early universe from density fluctuations, and their masses were smaller than the mass of the sun, then we would have very high temperature black holes which would be evaporating, and they would be evaporating by giving out radiation in the form of black body radiation. This process is non-unitary, and therefore quantum fields in curved geometries is a strange game. It is not something which we can understand or explain with our standard stories of particle accelerated smashing of protons, which gives us the renormalization flows of QCD, QED, and so forth. So quantum mechanics, even in the presence of gravitational physics or curved geometries, is a strange story. Now, if we really think very deeply, then we see that perhaps this is something which is normal, because quantum mechanics and quantum field theory are defined for inertial observers. That is, they are special theory of relativity compatible, the theory which Einstein formulated in 1905, and they are not compatible to the inclusion of accelerated observers. If we include accelerated observers, which is the story of curved geometries, or we have curved geometries and we have particles interacting with each other in curved geometries, which means that they are accelerating with respect to each other, the quantum vacuum is not the same as it would be in a static observer's measuring frame. And we have to do something to our quantum field theory to include acceleration. Now, I have a formulation of quantum field theory for accelerated observers. And this theory tells us that if we have an accelerated observer in a flat background, that is, we are still without any gravitational physics in the system. So there's no interaction which is caused by massive particles. So we just have a probe, massless particle in a flat background in no gravitational interaction system, but the observer is accelerating. Then for that accelerated observer, half of the world does not exist. That's known as the RINDLER geometry. That is because some of the geometry becomes causally disconnected for the accelerated observer. Not only that, for that accelerated observer, in one half of the geometry, and this is very much true, time flows backwards with respect to the static observer's time, and on the other half, time flows forward. And the way we solve this strange situation is that we do quantum field theory in only one half of our space-time, and we take the region where time flows forwards and work with the quantum field in that section of our entire universe. And that basically traces out the quantum field in the other half, and that is why we have thermalization. The reason that we have particles or we have temperature controlled behavior of the quantum fields in curved geometries or in the presence of accelerated observer, in this example is just an accelerated observer, is because we are ignoring information about half of the quantum field to which we have no access. And this thermalization process can be understood using a formulation in complex physics by a Russian physicist who was actually at Brussels. When I was in Brussels, he was there. He was the chair of the Solvay Institute there. Then he died, and in his memorial lecture, ECG Sudarshan came. So that's how, when I went to listen to ECG Sudarshan's lecture, I got to know about Prigogine's work. And later, when I was working with understanding Hawking radiation using background independent quantum gravity, I found that the equations which I was using was Prigogine's equations. And it is a very interesting formulation. So what I found was that the accelerated observer's density matrix, I'm using the word density matrix, it is basically the outer product of the vectors in quantum mechanics, and it's the operator form of representing the quantum state of a particle. If we take the density matrix of the particle in the Minkowski space, then the accelerated observer's density matrix is a Prigogine transform of the Minkowski density matrix. And this transform is a very well-defined transformation implemented by operators which are known as star operators, star unitary and star Hermitian operators. What is so unique about them? In quantum field theory and in quantum mechanics, we use unitary operators or Hermitian operators to evolve the system, to transform the system. And we use those operators because they conserve probabilities. But in the Prigogine formulation, where there is the use of the star Hermitian operators, what we have instead of Hermitian or Hermitian conjugation is a star Hermitian conjugation, where when we take the transpose and complex, when we implement it on a matrix, the Hermitian operation studied in very technical terms is taking a matrix, taking the transpose of the matrix and taking the complex conjugate of all the elements of the transpose matrix. And we implement this in a star Hermitian operator, which is dynamical. We also reverse the time. And that is implemented by taking the Liouville operator, which implements time evolution for density matrices, to its negative. So star Hermitian operation is taking the Hermitian conjugate and then changing the direction of time from plus to minus, which can be implemented by changing the Liouville operator's sign from plus to minus. So when a theory is invariant under the star Hermitian operation, we have a new theory, and that theory has the information about the accelerated observer in the system, because obviously when we have the accelerated observer, half of the space-time sees time flowing forward, half of the space-time sees time flowing backward. However, physics should be the same for both the halves, and if we have a system which is invariant under star Hermitian operations, then we would be able to include our accelerated observer in our story. But what happens when we include the star Hermitian operation in our story? This is going beyond quantum mechanics, because quantum mechanics has only unitary operators, only Hermitian operators. In my formulation of quantum field theory with accelerated observers, we have star Hermitian operators, star unitary operators. The time evolution is implemented using a star Hermitian operator. The transformations within the Hilbert space are implemented using star unitary operators. What happens when we use this new operators, new set of operators? What happens is the phenomenon of entropy creation. For example, if we take the Liouville evolution of a density matrix and we transform it to this star Hermitian system, where the time evolution is now implemented using a star Hermitian operator, the time evolution breaks up into an even part and an odd part. The even part is something which we are used to. The odd part is also something which we are used to, but not in quantum field theory or quantum mechanics. What is this odd part? If we look at Boltzmann's H theorem, which describes the flow of an ideal gas where entropy is generated, or we have the theory of irreversible flows and the fact that entropy always increases with time, we have a flow in which in one term we have reversible Hamiltonian flow, and in another term we have the collisions, the randomness of the system becoming manifest, and that gives us the irreversibility of thermodynamics and Boltzmann's H theorem. So what we are seeing in the star Hermitian and the star unitary formulation of quantum field theory and quantum mechanics is the process of irreversible flows emerging, is the process of entropy creation naturally emerging from the formulation. However, as we said, this is my work for an accelerated observer on a Minkowski background. In quantum gravity, in its complete formulation of quantum gravity, the Minkowski background is also an emergent background. It is something which is not given to us as for granted, but it's something which is fluctuating in the quantum formulation. It is something which is emergent from a underlying quantum theory of gravity. So we have to use the background independent version of this theory to really probe this aspect of quantum field theories on curved geometries, and what it is saying about nature of quantum gravity, that it should, by its own formulation, be entropic. The formulation of quantum gravity should allow for entropy production, should allow for something more than probability conservation, and should have some sort of entropy or the concept of time flows inbuilt in its inherent nature. To probe that in its true form, one has to use background independent versions and test for the existing background independent versions in the current systems. Now, how do we know that a system is quantum? If you look at the initial discovery of quantum mechanics, it was because we had to explain black body radiation. What is black body radiation? it is the thermalized electromagnetic quanta, and this exchanges energy in units, integer units of Planck's constant h times the frequency of the electromagnetic quanta. This is a very strong formulation, and if we look at the quantum field theoretic version of the quantization of light, we have the Fock space quantization, and the energy or the Hamiltonian of the E and B fields are related to the sum of the squares, and it's actually a simple, in fact, an infinite sum of harmonic oscillators of the E and the B fields. If we try to write the same story for gravitational waves, because they've been discovered recently, so we are sure in gravitational physics we have the same wave phenomena as electromagnetic waves, and whether we would be able to quantize the system is the next question. If we try to quantize gravitons and find gravitons, it would give us the theory of a Fock space basis for the graviton, which is a two-indexed metric, very weak in its formulation. However, when we try to study its energy, there's no concept of local gravitational energy. So there's one deviation from electromagnetic theory, and also the fact that if we take quadratic terms to formulate the gravitational Hamiltonian, we would find interactions. These interactions all are infinite. Gravitational theory, when we try to quantize it using perturbative methods, which works very fine for QCD, QED, is non-renormalizable. So we really cannot talk about quantum gravitational wave or gravitons. We've not detected that there is a mass bound. However, if we try to formulate it, we would have to formulate the theory of graviton as in a theory of quantum gravity, where the Minkowski background over which we are perturbing is obtained in the semi-classical limit of the theory of quantum gravity. For background independent gravity, we have various formulations, and one is known as loop quantum gravity. This is formulation of gravitational physics as a Yang-Mills theory. There are semi-classical states in loop quantum gravity. I'm running out of time, so I'm just going through the slides. And what we find is that we can formulate classical geometries as limits of a quantum mechanical state called the coherent state, and we can write coherent states for black holes. For example, I wrote a set of coherent states using the work of Tiemann et al. They were done when I was quite young, actually, 2003 and 2006 papers. And the coherent states are very similar to the coherent states you see in harmonic oscillator quantum mechanics formulations, except that they are non-abelian in nature. So there is some difference. And what was observed in 2013 was in a paper which is published in the journal Symmetry, Integrability, Geometry, Sigma, is that the flow at the horizon which generates Hawking radiation is PRIGOGINE. So it seems that the semi-classical probe of the quantum gravitational phenomena is indicating that we have to be more than our unitary and Hermitian quantum field theory. Now, very recently, there was the story of the image of the event horizon. This is a photo. It's a photo of a black hole M87 obtained using infrared telescopes, very long base interferometry. In fact, there are 8 telescopes and data from 8 telescopes were gathered from probably 2011, and they could filter out all the other details and plot photon trajectories around a black hole. This is all we have for the black hole, because everything which falls inside it is lost, so we cannot see inside the black hole, but whatever is circulating outside it can be seen, and we can see coarse-grained structures appearing in the system. Now, what is this image? The physics of it is quite simple. We study the trajectories of particles outside the black hole using geodesic equations. We know how to solve them. And there is something called the critical impact parameter, which appears because of the maximum up to which the photon can go near a black hole. After that, it's trapped inside the black hole geometry, but it's outside that critical impact parameter, it can still escape to infinity. And it is those which escape to infinity that we observe. And these photons have a very strange, interesting phenomena, and that is they can circulate once and come back to us, but they can circulate twice, thrice, in fact, n number of times before they emerge again. And this is the reason we have this structure which is generated. These calculations you can find in the book by Chandrasekhar or in this paper by J.P. Limine in the early 80s. So this is very well-known phenomena which we are seeing being imaged by the Event Horizon Telescope collaboration. Now, if we have our gravitational coherent states, which are basically semi-classical states in a background-independent quantum gravity theory, then this geometry of the black hole gets corrected because of quantum fluctuations. And these corrections are non-perturbative from the point of view of semi-classical physics, because these are not generated by fluctuating quantum fields or back reactions, but they are inherent to the formulation of the quantum gravitational physics. And in a recent paper with the summer student, Swamsiddha Maharana, we showed that if we take into account the corrections due to the quantum mechanics of the geometry itself, we have very interesting behavior. In particular, if we look at orbits which are far away, then the equations which relate the orbits to the distance from the critical impact parameter are linear as expected. But if we zoom in, then after a particular value, the orbits bounce off. This is expected in a typical quantum behavior because there's quantum pressure, which is repulsive, and that is the reason we have atoms. And this is what we see even for the Event Horizon Telescope. And there is some sort of quantum number which we can associate with this system, after which the orbits which were circulating around the horizon, instead of circulating further, in particular, if we look at the J.P. Limine paper, they're supposed to circulate infinite number of times around the horizon before emerging again. We, in our formulation, find a cutoff to that infinite number of circulations around the horizon. We find that, for example, a solar mass black hole, this number is 26, and for a M87 black hole, this number would be 475. So photon can orbit only 475 times round the horizon and not infinite times round the horizon. Now, whether this is true or not, obviously can be seen from these images. And this image, which has some coarse graining apparent in it because of the measurement of the polarization, came out in March 2021. So we are still working on it to see if we have found something which is fundamental and something which is due to quantum formulation of gravitational physics. There is also other ways of probing the true nature of quantum gravity, and that is using analog models, that is using models in condensed matter in the lab, for example, Bose-Einstein condensates, which simulate predictions from semi-classical gravity. And in particular, there was a work by Jeff Steinhauer in 2019, and then we are trying to formulate and emerge as a big collaboration with Alfredo Yerio in Prague, because, and this is where I will end, because I wrote a paper in 1998, which was when I was a young graduate student in math science in Chennai, which was about Hawking radiation from a three-dimensional black hole. And at the time, obviously, I knew that three-dimensional black holes do not exist. Life is four-dimension. But I still wrote it from the point of view of academic interest. However, when we try to simulate a black hole using a graphene sheet, then the graphene sheet is two-dimensional and time is one-dimensional. So it's 2 + 1-dimensional system. And if we are able to test this in the lab, we would be testing my paper written in 1998. So you never know what time and what place your work gets to be useful. So according to me, yes, it is time for quantum gravity phenomenology. That is when we design experiments and we test for nature to agree with our predictions. And we are publishing a volume on quantum gravity phenomenology. If anyone's listening to this talk and they would like to contribute to this volume, our deadline is 31st October. Oops, it got shifted. It was earlier 30th June. We've changed it to 31st October. So we are still accepting submissions. And we have interesting papers, in particular in loop quantum cosmology, in astrophysical implications of quantum physics, and also gravitational waves in this volume. So we hope that this volume would be useful for anyone who wants to begin in this field of research. Okay, I will end here now. I'm 13 minutes over time, but I think I will be forgiven if I can bring up the streaming.
Okay. Thank you, madam, for your wonderful presentation. So if you allow, we can start our discussion session. So
Yes.
we have got few questions in comment and few questions in inbox. So if you allow, I can start from the inbox first and then I'll go in comment.
Yes.
So first question, what is time wrap?
Time warps, not time wrap, it's time warp. So in our day-to-day life, if we have a clock, then time flows in Newtonian physics, independently of space-time. But if we have general relativity, in particular even for our Earth, then time as measured by the clock is different from the time measured in a reference frame. Let's say we are sitting on Earth and there's a satellite which is going around the Earth, then the time measured on our Earth is different from the time measured on the satellite because we are located differently in the geometry of Earth's gravity, and that is known as time warping. And we know that there is evidence for that because we have to adjust for it when we build our GPS systems. If we didn't adjust for time warping, warping means twisting, sort of curving time, then our GPS would give totally different predictions.
Okay, madam.
Uh,
So,
and we have extreme time warping in presence of black holes, causality changes, light concept, and also when we have time travel. But that is something which we can discuss in details, or you can read from reviews on time travel, or just read about GPS. You will understand what time warping is.
okay, madam. So, we have got another question. So, what is the accretion disk?
Accretion disk. Yeah, this is a question for an astrophysicist. But an accretion disk is when we have matter falling into the black hole, then the fall into the black hole is not like, falling at all angles, but there is sort of disk formation around the black hole because of the gravitational fields around the black hole. And we can observe these disks rotating and falling into the black hole because of the geodesics which the particles are allowed to be in. But of course, if there's too much of matter, then we model the geometry and the matter interaction using hydrodynamical equations. So it's a complicated system, but it's like a disk, yeah.
Okay, madam. So, this will be the last question in inbox. So, how can we take photo of black hole?
How can we take a photo of black hole? That is, yeah, we cannot take our cameras and go near it and click it, because obviously don't try it, it's dangerous. But sitting on Earth, we can focus our telescopes towards a region where there is expected to be a black hole, in particular at the center of this galaxy, which we call M87. And these telescopes are infrared telescopes, so they have very large wavelength electromagnetic waves which are being detected there. And then we gather the data from 8 different telescopes, and we have various algorithms to filter out various signals and keep the ones which are from the photons which are orbiting the black hole. And when we keep those, we get the image which has been published in the recent work by the Event Horizon Telescope. So if you want to explore that image, you can basically Google Event Horizon Telescope and visit their website. They have non-technical introduction to their algorithm and filtering and so forth. I don't know which level you are in. Probably you are very technical. You probably understand the technical descriptions of the system too. But it is something new. It is something which is happening, and definitely a very interesting area of research to work in.
Okay, madam. So, now we can go in the comment section. So, for the first question, if dark matter is a single entity throughout the universe in form of continuous lines like web of spider, then we can express the curved spacetime in terms of increase of mass density of dark matter. Will this concept help to solve problem of unification of gravity with quantum mechanics?
I have never heard about webs of a spider and dark matter. In fact, what I have heard about is maybe dark energy. Dark energy being inherent to the fabric of space-time. So I must mention that the quantum gravity, the background independent quantum gravity, which I was talking about, and the coherent state which I was talking about, is solved in matter vacuum. So matter is vacuum, matter is in a vacuum state. It's geometry which is quantized. In general relativity, the black hole metric is a vacuum solution to Einstein's equation. So dark matter is a different story. Quantization of geometry is a different story. That's a vacuum for matter. And if we can see weave-like geometry at Planck length scales, then that would be not because there's matter there, it's because geometry itself is coarse-grained. Geometry of space-time, and this is very important for all of us to understand, space-time is not matter. Space-time is not something quote and unquote, which is mass, or even energy. Locally, space-time doesn't have any energy. It is just the fabric of our cosmos. Philosophically, it's anything in which we can put matter in. But when we try to probe it at length scales which are Planckian, then we cannot put matter at every point as if it was continuous space-time. Our matter can exist only at discrete set of points, and our measurements of the geometry of space-time, which is obviously done using a probe, would also give us quantized area and volume.
Yeah, thank you, madam. So we have another question from him. So current experiment on size of neutron confirm that neutron star can't compress beyond certain limit. Then what is the mechanism beyond creation of black hole from neutron star?
Is this something to do with the Chandrasekhar limit? That is already, a Nobel Prize has already been obtained for that by Chandrasekhar, so perhaps I'm no longer interested in this. Or maybe you should ask a new question to get a Nobel Prize for that.
Because the same person has asked another question, and this is also maybe the similar question. If effect of gravity is expressed in terms of the increase of mass density of dark matter instead of Newtonian term of massive object, will normalization become possible for gravity?
I don't know why dark matter is so favorite. Yes, we still don't know what dark matter is. What you're saying is that can gravity be renormalizable? And answer is yes. If we add higher order terms to gravity. Can I bring up my slides again?
Yeah, of course, of course.
Okay. So I didn't have time to describe this in details because even though in my abstract I had said I'll talk about gravitons, I decided to talk about the thermal story more than the story of gravitons, because the thermal story probably you haven't heard so much emphasized before, the fact that gravitational quantum would have to have some sort of entropy in it. So if we look at this, then can you see the slides, Pretam?
We can see.
Oh, okay. Sorry. So if we look at the gravitational action, then it has square root g times r, the Ricci scalar, in the action, which gives us Einstein's equation, and it has been tested to great details. But if we include square root g r squared term, then perturbative gravity is renormalizable, if that is what your question is. Is it about renormalization of gravity, or is it something else? Normalization, I hope you mean quantum, something to do with quantum gravity. But of course, mass density of dark matter is there in our energy momentum tensor. Otherwise, we wouldn't have our cosmic story today. To bring in cosmic story, which has acceleration in it, and also the fact that there is anomalous behavior of rotation in galaxies, we had to bring in the dark matter in the Einstein's equation. So the dark matter is used as a source of gravitational physics in the Einstein story.
Yeah, thank you, madam, for your wonderful presentation and a nice discussion session, madam. So I think our students have learned a lot of things about the quantum gravity phenomenology. The main aim of our program is to motivate our student in this corona pandemic situation. And as you have started by motivating speech, so and your lecture, I think many of our students may motivated by your lecture. So thanks again. So it's a great webinar with you, madam, and we are very grateful to you for giving us time and for giving me opportunity to attend such an important webinar with you, madam. So
থ্যাংক ইউ, নমস্কার। বাংলায়
কেন
কথা বলা হলো না, কিন্তু
হ্যাঁ, অবশ্যই।
বাংলায় ডেফিনেটলি কথা
অনেক ধন্যবাদ ম্যাডাম আপনাকে যে আপনি
ঠিক
সময়
আছে।
দিয়েছেন। ভালো থাকবেন, এভাবে আমাদের মাঝে আপনার জ্ঞান বিতরণ করে যাবেন। ভবিষ্যতে অবশ্যই আমরা আশা করব যে আপনাকে নিয়ে আমরা সামনাসামনি কোনো একটা সেশন যদি করতে পারি, তাহলে অবশ্যই ভালো লাগবে আমাদের এবং আমাদের বিভাগের ছাত্ররা উপকৃত হবে। ভালো
ডেফিনেটলি
থাকবেন।
তুমি ভালো করে কাজ করো এবং আশেপাশে স্পেশালি মহিলা ছাত্রীদের একটু এনকারেজ করো যে তোমাদের দরকার সায়েন্স কন্ট্রিবিউট করা, এবং বাংলাদেশ থেকে একটা নোবেল প্রাইজ আসুক, সেটা কামনা রইল।
বাংলাদেশ তো পেয়েছে শান্তিতে, এখন সায়েন্সে যদি পায় সেটা।
সায়েন্সে
জি জি
আমাদের
জি
দেশেও
জি ম্যাডাম।
কারেন্ট যে সায়েন্টিস্টরা আছে তারাও নোবেল প্রাইজের জন্য চেষ্টা করছে। আমাদের দেশ বলছি কারণ আমি এখনো ইন্ডিয়ান সিটিজেন। কানাডায় তো খুব রিসেন্টলি, কানাডায় যেখানে আমার কর্মক্ষেত্র, সেখানে ডনা স্ট্রিকল্যান্ড নোবেল প্রাইজ পেলেন, তাতে আমরা খুব খুশি হলাম। তোমাদেরও এরকম হোক, সেটাই আশা
জি
রইল।
ম্যাডাম, আশীর্বাদ করবেন ম্যাডাম, ভালো থাকবেন, নমস্কার।
নমস্কার।